and the talk will be given by Jieming Mao.
All right. Thank you. This is a joint work with Mark Braverman and Yuval Paris. So in this paper, we consider the following problem. There are n items with an underlying order, and our goal is to learn the set of top k items together with the rankings of these key items by making pairwise comparisons. So we call this problem sorted top k. Here are some examples about why we care about this problem. So for example, a recommender system usually recommends to users a list of items chosen from a much bigger set, and these items are displayed in a certain order. Another example is that in a sport tournament, teams compete with each other, and in the end, we care about which teams are the top teams, and also we care about the rankings of the top teams. Okay. So this problem can be solved by first finding the set of top k items, and then sorting these key items. So this takes O of n plus k log k comparisons, and this is optimal up to a constant factor. One thing to notice here is that this algorithm needs to make adaptive comparisons. By adaptive, I mean that in the algorithm, which items to compare sometimes may depend on the previous comparison results. And however, in some applications, we only have limited number of rounds. In each round, comparisons need to be made simultaneously. So this simple algorithm doesn't work here. And in this paper, we try to understand how many comparisons we need to make in order to solve sorted top k in R rounds for some constant R. So we first consider the simple case in which comparisons are noiseless. So in this case, the comparison results are always consistent with the underlying order. So here's our result. We show nearly tight bounds for sorted top k. And as you can see, the same problems for top k and sorting have been already studied in previous work. Actually, most of these results are done 30 years ago. So now I'm going to show you some main ideas for obtaining the results for sorted top k. For algorithms, the main idea is to use pivot items. So in the first round, we just randomly pick some items and compare them to all items. And by looking at the comparison results, the entire set will be partitioned into chunks of items with consecutive ranks. And we know which item is in which chunk. So in our algorithm, we just, in the first round, we just use these pivot items. And in the rest R-1 round, we use the R-1 round sorting algorithm in each chunk that contains top k items. So this algorithm actually gets the optimal number of comparisons when k is larger than the average size of a chunk. When k is small, it's more complicated. I'm not going to talk about it. So for lower bound, we use techniques from bounded round sorting lower bound. The main additional observation is the following. So the difference between sorted top k and sorting k items is that in sorted top k, in the very beginning, we don't know which k items we need to sort. So it's not hard to see that in the first round of sorted top k, at most the k squared over n squared fraction of the comparisons are made between top k items. And this implies that sorted top k is harder than sorting k items with imbalanced number of comparisons. Basically, in the first round, there are fewer comparisons. And based on this observation, we can extend the sorting lower bound into a sorted top k lower bound. Okay. Again, this argument only works for large k, and for small k, we need to do something different. All right, so in this paper, we also consider a case in which comparisons are noisy. So in this noisy case, each comparison is correct with probability 2/3. And our goal is to output correctly with probability at least 2/3. For 1 or 2 rounds, we show tight bounds for these 3 problems. Compared with the noiseless case, sorted top k gets an extra log k factor. Top k bounds don't change, and sorting gets an extra log n factor. So I just talk about the one-round algorithms. First one is the one-round sorted top k algorithm. We can use n squared, O of n squared log k noisy comparisons. So algorithm is actually very simple. We first run the top k algorithms with O of n squared comparisons, assuming you already have it. And in the same round, we also compare all pairs log k times. So it's not hard to see that this algorithm outputs correctly if the top k is computed correctly, and also the majority of comparisons for each pair in top k is consistent with underlying order. And notice that here we're only looking at k-choose2 pairs. So by repeating each comparison log k times will be enough to achieve a good overall successful probability. And as you can see here, this sorted top k algorithm highly depends on the top k algorithm. So how do we actually find a set of top k items with only O of n squared noisy comparisons in one round? If we, so with this many comparisons, we cannot compare all pairs log n times. So again, we use pivot items. So we just randomly choose n over log n pivot items and compare them to all items log n times. And by looking at the comparison result with high probability, we will partition the entire set into chunks of size roughly log n. Okay? And there will be a chunk which contains the case item. So for any item that is not in that chunk, we know whether the item's in top k or not. So after these comparisons, we are left with roughly log n items. And how do we deal with them? So we will hope that we have some more pivot items to further partition this chunk. So we just use a second level of pivot items. We pick n over log n pivot items and compare them to all items log n times. So there are two things to notice here. First, this second level pivot items are only used to deal with the log n items left in the first chunk from the first level. So repeating each comparison log n times will be good enough to achieve an overall good successful probability. The second thing is that although we are analyzing these comparison results sequentially, we can actually make all these comparisons into a single round. So by further extending this idea into multiple levels of pivot items, we can get a one-round top k algorithm with only O of n squared noisy comparisons. All right, that's it. Thank you. I think we always allow randomness. The lower bounds for random algorithms. Yeah, I don't know.
So when your noise model is independent random noise comparison, right?
Yeah.
Have you considered having a constant fraction of errors that actually are fairly good? That'd be a more difficult model, but it should
Yeah,
be
that sounds
possible.
more difficult, yeah.
I kind of expect it's a little bit more consistent with the way learning works, because typically errors are very correlated to random reports.
Right, I guess for that noise model, you need to change your goal. Basically, with that fraction of noise, you can completely screw a pair of consecutive items. But yeah, I guess probably you can make more. Yeah, yeah.
Top one.
Right.
We know that if you do n log n comparisons, you can tolerate a constant fraction.
Right. Yeah, that's an interesting question.